channel. Today we're going to work on the question Evaluate Division. The question states you are given an array of variable pairs equations and an array of real numbers values where equations I equals AB and values I represent the equation A divided by B equals values I. Each AI or BI is a string that represents a single variable. You're also given some queries where query J equals CD represents the jth query where you must find the answer for C divided by D. Return the answers to all queries. If a single answer cannot be determined, return -1. Note, the input is always valid. You may assume that evaluating the queries will not result in division by 0 and that there is no contradiction. Let's look at the example. Example 1, input equations equals A, B, B, C, and values equals 2, 3. So this means A divided by B equals 2 and B divided by C equals 3. And queries include A, C, B, A, AE, AA, etc. So AC, let's look at AC. So we know that A divided by B equals 2 and B divided by C equals 3. Let me write this down so it's easier to explain. So when we know A divided by B equals 2, what does this also tell us? This also gives us B divided by A, right? Which is 1 over the result of this, so it's 1 over 2. And when we know B divided by C equals, when we know B divided by C equals 3, we also know C divided by B, like it backwards, right, equals 1 over 3. And then, so it's asking us query what's 1 divided by C. So 1 divided by C is actually 1 divided by B times B divided by C. So it's 2 times 3, which is such, and the answer is such here. And let's look at the next one, B divided by A. So B divided by A is just 1 over this answer, so it will be 0.5, which is correct. A divided by E, E doesn't exist in our equations, so we return -1 because it's not possible. It states if it cannot be determined, return -1. And then A divided by A itself will always equal 1, so it's 1. And then X divided by X equals -1. Although it's dividing itself, it should equal 1, but since X is not previously determined in equations, we just return -1. So yeah, this is our answer, and then with this we can start writing. This is a graph. This question, the solution can be represented using graphs. I'm thinking today we'll be solving this using a DFS. Let's start. So first I'll be creating a dictionary of dictionaries, and I'll be using the help from collections. From collections, import default dictionary, and then I'm gonna define my graph as a default dictionary of dictionaries. So this basically means with the help of default dictionaries in the dictionary, it's basically a dictionary inside a dictionary, and the first key in our dictionary would be this first node, right? And then the second key will be the node it links to. Everything it links to will be in there. So this actually helps us, like when we're searching in the first node, we can look at all its neighbors, like by just doing for node B or for neighbors in graph A, something like that, so we can easily search into the neighbors of that dictionary, that specific dictionary. Or word it betterly, searching from that source to its neighbor destinations. Yeah, so first of all, let's parse our input, which is equations is like 2 together, and then values is 1, and this one is assigned to these two. So I can use something called zip to parse it. So for what do we call these nodes? I'll just call them A and B, and then V as in the value, and sub equations, comma, values. So basically this parses it into A, B, and V. So after we parse it, we want to populate our graph with these values. So what we can do is graph A, B equals V, and then we also know the opposite, right? So B, A equals 1 over V, because AB equals a number, and then BA will automatically equal 1 over that number. And so we're done populating our graph. What do we want to do after? I guess we can start writing our DFS. My DFS will take node A, node B, and then node A will be like the source, node B will be like the destination, and then we'll keep a visited set too, so we don't visit the ones that we already visited, so we don't get into like a loop. So we can do some base check, something like A not in graph or B not in graph. Return -1. So like when it's not even part of this graph, that means it's something like, you know, X or E, then we just automatically return -1. We don't need to search any further. We can do another base check. So if B in graph A, then that means we can just return graph AB. And then now we are ready to search in the neighbors. So for neighbors and graph A, if neighbor not in visited dot add neighbor, and then we can do temp equals, we can run the DFS. The source would be the neighbor now. Destination would still be B, and then we pass in our visit set. And then if temp equals -1, then we just continue. It means that path is not valid. We don't need to search any further. And then else we would return temp times graph neighbor P. And then if we've searched all the neighbors and then we haven't gotten anything, we return -1. And now we can actually put in the query. So result is an empty list for A, B, and queries. We can call our DFS. So DFS A, B, and then an empty set, and can do results.append this, and then in the end we return our result. So this shouldn't be neighbor B, it should be graph A and then neighbor. So it times its original to its neighbor, and then it times whatever neighbor to the next neighbor until we reach B. So it'll be a sum of all these things that we times it to itself. And this should be the correct code. Yeah. Wow, it's actually faster than 96.59%. Please let me know if you have any questions. Thank you for watching.